Hi, ladies and gentlemen. Let me welcome you to the 16th session on ECT 204 Signals and Systems. In this session, I tell you about the solution of linear constant coefficient difference equation. In the last class, I told you a linear discrete time system or LTI discrete time system is modeled with a linear constant coefficient difference equation. Now here we will see the solution of LCCDs. The speech is organized into your learning outcomes, then the solution of linear constant coefficient difference equations, and the summary of understanding. Here you will learn to solve LCCDs. When it comes to linear constant coefficient difference equations, the general solution of a linear constant coefficient difference equation is yn equal to yhn plus ypn, where this yhn part, that is a homogeneous solution, that is a response to of the system to initial conditions, assuming that the input xn is 0. That is, the homogeneous solution yhn is the output of the system without any input. That is so the output or the response is the response of the system is to only initial conditions. Okay. Now the second part, that is the particular solution ypn, that is a response of the system to the input xn, assuming 0 initial condition. Now there are no initial condition, only the input x is there. I can do this because this is a linear system, because the sum of the response is the response of the sum. Now, this method of solutions is rather unpopular. Mostly we use a Z transform for doing that. That we will discuss in the towards the end of this course. So, but this also you should know. The homogeneous solution is found by solving the homogeneous difference equation, that is without any input, xn equal to 0. That is yn plus k equal to 1 to n alpha k yn minus k, that is equal to 0. That there is no excitation, x equal to 0. Now here you assume a solution of the form yhn, that I assume that my homogeneous solution of the form is z raised to n, so that substituting this solution in this equation, this becomes z raised to n plus k equal to 1 to n alpha k z raised to n minus k, that is equal to 0. Now if I take out a part here, that becomes if I take out p zeros, that is this z raised to n minus p into z raised to p plus alpha 1 z raised to p minus 1 plus alpha 2 z raised to p minus 2 plus etc. alpha p equal to 0. Okay. Now this solution alpha raised to p plus alpha 1 z raised to p minus 1 plus etc., this is called the characteristic equation. This may look very strange to you, but if you do one problem, it will be very clear to you. Now, when you look at the homogeneous solution, what is a homogeneous solution? Yhn, that is k equal to 1 to n, ak z raised to k, zk raised to n. That is the homogeneous solution, that is the second part of the solution without any initial condition, that is with some input xn, that is I'm talking about the homogeneous solution, sorry. So z raised to n, this homogeneous solution, now it has to be written as yhn, that is k equal to 1 to n, ak z raised to n, or zk raised to n. Now this constant ak are chosen to satisfy the initial condition. Now this is a response to the initial condition, not xn. Now with a repeated root, the homogeneous solution will look like this. Yhn, that is equal to a1 plus a2n plus etc. am n raised to m minus 1 plus m plus 1 to n, ak is raised to n. Okay. Now if you do a problem, that will be very clear to you. Now for the particular solution, that is for the second part of the solution, it is necessary to find the sequence ypn that satisfies the difference equation for the given input excitation xn. So now there's a table for this particular solution. For most commonly encountered inputs, some particular solutions are given. This you have to know. Suppose the input is a constant, xn is a constant c, then the particular solution will be a constant, say c1. If the input excitation is cn, this will be c1n plus c2. You have to find c1 and c2 by putting some initial conditions. Or if it is some power sequence c a raised to n, it will be c1 a raised to n. If it's a cosine function like c cos n omega 0, then the particular solution will be c1 cos n omega 0 plus c2 sin n omega 0. If it is a c sin n omega 0, if the input excitation is a c sin n omega 0, the particular solution will be c1 cos n omega 0 plus c2 sin n omega 0. Now suppose it's a combination of the power signal and a cosine signal. Suppose it is a c a raised to n cos n omega 0. It will be c1 a raised to n cos n omega 0 plus c2 a raised to n sin n omega 0. If the input is an impulse, then there is no particular solution. Now let us consider the difference equation yn minus 0.25 yn minus 2 equal to xn. Suppose that the input excitation is a un, that is a unit step, assuming the initial condition y minus 1 is 1 and y minus 2 equal to 0. Okay. Now my input output, so the input value is a constant from n equal to 0 onwards, it's a constant. So my particular solution is a c1. So ypn, the particular solution is c1. Now if I substitute in this equation, you can see that yn is c1 minus 0.25 c1. Okay, that's equal to 1. So that makes 1 minus 0.25 is a 0.75. So c1 is a 4 by 3. Now I have to find the homogeneous solution. So for homogeneous solution, I can set yHn is the homogeneous solution as z raised to n. Now how do I form the characteristic equation? This as an order of 2. So this becomes z raised to n, z raised to 2. I'm sorry, z raised to 2 minus 0.25 is a 0. So that is how I form the characteristic equation. You have two delays here. So it becomes a power of 2. So it is z square minus 0.25 is a 0. This is how I form the characteristic equation. So I have the roots for this characteristic equation as z is plus or minus 0.5. So I can have the homogeneous solution as I have seen the homogeneous solution here. It is of the form ak z raised to n, k from 1 to n. If there are no repeated roots. Now I don't have repeated roots here. So yh and the homogeneous solution will be a1 0.5 raised to n plus a2 into minus 0.5 raised to n. Now the total solution for this is yn, that is yhn plus ypn. So it is 4 by 3 plus a1 into 0.5 raised to n plus a2 into minus 0.5 raised to n. Now I have to find this a1 and a2. For that I have to apply some initial conditions. Some initial conditions are given here. Y minus 1 is 1 and y minus 2 equal to 0. So I put it here. y0 that is 4 by 3 plus a1 into 0.5 raised to 0 plus a2 into minus 0.5 raised to 0. That is 4 by 3 plus a1 plus a2, that is a 1, because we said y0 is a 1. Then y1 is a 4 by 3 plus a1 into 0.5 raised to n plus a2 into 0.5 raised to n. So that is a1 into 0.5 minus a2 into 0.5, that is a 1. So solving this equation, I get a1 equal to minus 0.5 and a2 is 1 by 6. So that my solution becomes yn is 4 by 3 minus half of 0.5 raised to n plus 1 by 6 minus 0.5 raised to n for n greater than or equal to 0. So I can write it with the un also. I can say that yn is 4 by 3 un minus half of 0.5 raised to n un plus 1 by 6 into minus 0.5 raised to n un. This method is rather unpopular. People generally go for is a transform. That we will discuss later on. Now you learn to solve the linear constant coefficient difference equation. So you have two parts in a solution, the particular integral and my homogeneous solution. So you know how to compute that, and that is the end of this presentation. I thank you all.